First of all, thank you for the organizers for accepting my talk and for allowing for virtual participation. So my name is Idel Waisberg, and I'll be talking also about multiplicity of A stars, but actually a survey that we are doing in the south with gravity. So our interest in A stars stems from a slightly different corner than the previous speaker. So we're actually interested in their connection with white dwarfs. So in the left here, you see the initial final mass relation for white dwarfs. And we see that A stars with masses between 1.5 and 2.7 solar masses give rise to white dwarfs with masses between about 0.5 to 0.7 solar masses. And then if you look on the right, it shows the spectroscopic masses of white dwarfs based on SDSS sample. And you can see that the peak of the distribution is exactly in the range of masses that for A star progenitors. So we can say that A stars are one of, if not the most common progenitors of the white dwarfs that we see today. This is not surprising, given that they are more abundant than B-type stars, and also that they are their lifetimes are short enough to evolve within the age of the universe. So the multiplicity of A stars is inexorably connected to that of white dwarfs, and that's our main interest in this. And as the previous speaker said, the multiplicity of A stars is particularly poorly constrained when compared to other types of stars, and especially in this region. Especially in this region of 5 to 20 AU, which is at the moment only accessible with optical interferometry. And so we have some basic knowledge at separations of more than 20 AU from the De Rosa survey. At separations at a few AU, they can be found through spectroscopic studies, although they are very challenging, and many are not still not discovered. And then there is the sweet spot range for optical interferometry. So our target selection is also based on this vast survey by De Rosa, and we are limited to the south because we're using VLTI gravity. So our parent subsample is that of 108 A stars. However, we do apply a cut in order to select promising targets for 5 companions, and that is based on Gaia and Hipparcos proper motions. So I'll talk about, I'll detail that in this next slide. So what you see here is this is a Gaia Hipparcos proper motion plane. So on the y-axis, it's the difference in proper motion between Gaia DR2 and Hipparcos. Actually, it's the second one is not the Hipparcos proper motion, but actually the positional difference, the proper motion implied by the positional difference between Gaia and Hipparcos, because that's much more accurate than Hipparcos itself. And so this is a proper motion measurement over about 12 years, whereas in the x-axis is the proper motion change between Gaia DR3 and EDR3 and DR2, which have mean epochs differing by 0.5 years. And so what I plot here are all the sample of 108 stars. And you can see the stars that are numbered are the stars in our subsample that we are observing. So we selected the stars that have a proper motion change in the y-axis above 0.5 kilometers per second, because these are promising stars for having massive companions of about 1 solar mass, which is what we are mostly interested in. And you can also see in this plot that there are 2 main branches. There is one branch which is following this line where the Gaia Hipparcos change is about 10 times higher than the intra-Gaia change, which points to binaries with decade-long periods. And then there's also this other branch here where the proper motion changes are comparable. And so this points to stars that have periods that are shorter, about a few years, so that they could still be different in the two Gaia catalogs, but still long enough to not average out in each individual measurement. And so this subsample constraint was very successful. So out of the 9 targets that I have analyzed, so far we found 9 newly discovered stars. So it's a very high yield. And I'm just going to show you a few examples of what we found. So first of all, there is the bread and butter discovery of a binary. So for example, here, this was a star with a change in proper motion that was had no AO companion. And we found a new companion of 0.8 solar masses on a 1 AU orbit. We have some more extreme cases like this one. So this was a non-AO binary with a period of 10 years. And we found it to be a hierarchical quadruple. So each of the components is actually also a binary with a 0.8, about 1 solar mass companion. And you can see here from the data, the advantage of using gravity with the high spectral resolution is that we can resolve this high frequency components from the high separation, a large separation binary that would be very difficult to do with low spectral resolution. We also have this interesting case of just a question, is this, can you see the full screen, or is this Zoom thing blocking your vision?
No, I think we can see the full screen.
Okay, thank you. So, so this is an example where the 2 stars could be separated out in the gravity acquisition camera. So we could actually observe them, one with the fringe tracker channel and the fainter one with the science channel. And so the primary was a non-spectroscopic binary, which we also see in the gravity data. And then the secondary turned out to also be a closed binary. So the system got upgraded from triple to quadruple. So here another advantage of gravity is that you can observe fainter companions if they exist. And then here's another interesting example where we did not find a companion. So this was a star, an A star. It has an AO companion, which is an M dwarf binary, but that is too far away to cause the proper motion change. Yes, so in the gravity data, we see no signs of a companion, and we can put a flux ratio upper limit of about 1%. And this is another advantage of gravity, having the high spectral resolution. We also have a large interferometric field of view that can extend up to about 100 to 200 milliards seconds, up to the point where the light is not coupled into the fiber anymore. And so we could exclude the presence of any companion with mass above 0.4 solar masses within 200 milliards seconds, which is enough to overlap with the AO sample. So this is a serious analog for having a white dwarf as causing the proper motion change, although we cannot still completely exclude that it's a low mass companion that we could not exclude with the gravity data. And for the rest of my talk, I just want to focus on this one very complicated system. So recently put out an archive paper on this system. It's very complicated. So it deserved a full paper. So it's HJ 2814. So it was an A star with a companion at 20 arc seconds away. So on a 26,000 year orbit. So it's, and plus another companion that was seen in AO image, which turned out to be a background source. And then this star showed a proper motion change, so indicative of having more companions. And it also has, it's also spectroscopic binary. So it has this RV curve that we fit from purely based on archival data from FAROS and IRTF. And so we solved for its orbit, and it's a 13-day orbit, so it's way too short to cause the proper motion change because it's just averaged out in Gaia and Hipparcos. So we have evidence for two companions in this one causing the RV change and another causing the proper motion change. But when we looked at our gravity data, we saw evidence for no companion. So the data was compatible with a single star. Now, for the star causing the RV change, it just so happens that we observed it with the small AT array. So we were really not very sensitive to short separation companions. Luckily, there were archival pioneer observations of the star, actually observed as a calibrator, but we could turn it into a science target because there were other calibrators observed within the night in the same program. And so the pioneer data directly revealed this close binary companion. So that was solved the first riddle. So this close companion at 0.16 AU was just a 0.85 early K star. And we still had the second riddle, which star is causing the proper motion change. And the solution to that also came from archival data. So we look at the archival NACO data used in the ROSA. And unfortunately, whoever did the analysis actually missed the companion star at the halo of the A star. And so we could clearly see here it in all three NACO epochs. And so that solved the second riddle. That is the star causing the proper motion change. And then the companion that was actually resolved in the ROSA is this C star here. We also see it in our gravity acquisition camera, and we could actually measure its proper motion, and it's compatible with just being a background source. And so our picture for this system is that the A star was actually a hierarchical triple, and the companions were both around solar mass stars. Now, since we had all this data for this star, it's actually an opportunity to use interferometry for another interesting thing, which is to solve the dynamics of the system. So the interest in that is the following.
You have a minute left.
Okay, so our main interest in that was this very short period binary, 0.16 AU, and it's a riddle of how such a short binary can form. And so we investigated whether it could be from Kozai-Lidov oscillations induced by this triple system. And the reason we could do that is because this one astrometric point from Pioneer gives us, together with the RV curve, give us constraints on the orientation of the inner orbit. And using the NACO images and the Gaia-Hipparcos proper motions, we could actually solve for the outer orbit as well. And then we could just see, as a function of the allowed range of inner orbit inclinations, which is marked by these green contours, what is the maximum eccentricity that Kozai-Lidov oscillations could induce? And we saw that it's small for all allowed ranges. So this short binary is not undergoing tidal dissipations with its current eccentricity, and its eccentricity is also not being enhanced by Kozai-Lidov oscillations. And so this is a good candidate for a binary that just formed, a closed binary that just formed in situ through hydrodynamic interactions with the disk. Although we do have a complication of this outer binary, which is with a period of 26,000 years. And if that binary is on a very eccentric orbit, it could change the picture. But if it's not, it's a robust conclusion. So just to conclude, we have found that this selection that we used was very efficient. We found several high multiplicity systems containing A stars that are possible progenitors of white dwarfs in high multiplicity systems. This suggests that the multiplicity of white dwarfs is also underestimated, given that A stars are the major progenitors of the white dwarfs that we currently have. Yes, so thank you.
All right, thank you for the nice talk. It looks like we have one comment in the chat so far. Claudia says, if you didn't already, please mark HA 2814 Pioneer Calibrator in the bad calibrator catalog. So have you already marked it?
Sorry, I did not understand the question.
Oh, HJ 2814. There's a request to mark it as a bad calibrator in the bad calibrator catalog.
Oh, okay. Okay. Yes, all the stars could also be marked as, they are typically observed as calibrators. And yes, it also shows another technique that can be used to remove bad calibrators is just not only for A stars, but for stars in general, just using the Gaia-Hipparcos proper motion changes. Yes.
Okay, and there's another question from Renee saying, great results, just to double check. If I understand correctly, the proper motion anomaly is able to reveal milli-arcsecond binaries. What is the minimum separation in arc seconds that you can get?
So in the, you mean, if he means what we are sensitive in the gravity observations, it depends on which array we use. If we use the large array, then we can resolve down to, you know, fraction, like below a milli-arcsecond can be resolved. And because of the high resolution, high spectral resolution, we also have, like I said, a large interferometric field of view. So we are also sensitive simultaneously up to 200 milli-arcseconds, more or less. Yes. So
what about the detection on the separation from Gaia?
You mean what Gaia can detect?
Yeah.
So Gaia is complete to about more than 5 arcseconds mostly, and then below that, it depends on whether they could find a solution. So below that, below 5 arcseconds, it could or could not resolve it. And then I think the absolute limit, I think, is about 0.2 arcseconds, which is the PSF. Yes. So a comment on this is that Gaia DR3 is coming out, and it's supposedly going to solve for orbits in some of the systems. If they are just binaries, Gaia should be able to solve. So it would be an interesting comparison. If for this very complicated systems that are triples or quadruples, we'll have to see what Gaia does. Yes.
Okay, I think with that, we'll thank the speaker one more time and all the speakers in the session.